Hey, space nerds. This is NASA's Curious Universe. I'm your host, Patty Boyd, and today we are diving into some of the biggest unanswered questions in science. How did we get here? How did life start on Earth? Some of the answers could come from asteroids in our own solar system. So NASA sent a spacecraft called OSIRIS-REx to sample one, an asteroid called Bennu. In the 16 months since NASA scientists cracked open the sample canister, they've been carefully studying the rocks within. And now, finally, they're sharing some exciting results. In new research, the OSIRIS-REx team reveals Bennu carries organic molecules, the building blocks of life. We're going to talk about all of this with Jose Aponte. He's an astrochemist who works with the OSIRIS-REx team. He is one of the few people who gets to get up close and personal with Bennu. Jose, welcome to Curious Universe.
Thank you, Patty.
So, how did you first get interested in space and in studying asteroids like Bennu?
Wow, that's a difficult question to answer. I'm a chemist by training, so I got my bachelor's in chemistry, and I didn't know anything about space. I didn't have actually curiosity about space at all through my undergrad and later graduate school's studies. So I'm originally from Peru, and that's where I obtained my bachelor's degree in chemistry. And then I came to the States to pursue my PhD in organic chemistry. Mm-hmm. And so I saw this ad that they were looking for an astrobiologist to analyze organic compounds in meteorites. Mm-hmm. And so I was trained to analyze organic compounds in terrestrial samples. Mm-hmm. And I didn't know anything about asteroids or meteorites, but I found it really interesting. So I applied for that position, and that's where my journey at NASA started.
That's so cool. Was that the first time you had heard the word astrobiology, or did you have some sense of what that meant?
For sure. I didn't. I actually, I had to be honest, at first, the very first time that I read that word, I thought it was kind of fake. Mm-hmm. I had to go to Wikipedia and search it. And after reading about it, I thought, wow, this is the craziest, most exciting thing ever.
Totally. Very cool. So tell us a little bit about this asteroid, Bennu. What does it look like today? Where is it in the solar system?
So asteroid Bennu, it's a small object in the solar system that is orbiting between the Earth and Mars. And it's a rubble pile type of asteroid, which means that you can think of a bunch of different rocks that were put together and they aggregated into this body. And this mission, or REx, will help us understand how that rubble pile was formed and where it originally was created and what it contains inside.
Great. So before we get on to Bennu and what we're learning from Bennu, can you just sort of walk us through like the life story of Bennu? When did that rubble pile actually come together, and where do we think it was at that point in time? Like, what was its journey from the beginning of our solar system to where we are today, and how do we know that?
Okay, so that's a question that we didn't know before we went to Bennu. So it's a question that we are starting to answer only now that we are analyzing the samples, because we are discovering several organic compounds and several actually elements and salts and minerals that can only be formed in a place in the solar system where this type of compounds can solidify. Mm-hmm. We typically call that the snow line. It's where water in the solar system kind of freezes.
Can you just remind us like where the snow line is between like our favorite planets? Is it Jupiter to Saturn, sort of in there?
Well, before Jupiter.
Okay, so somewhere between Mars and Jupiter is where the snow line is. Okay.
And so if it goes farther inside the solar system, it becomes vapor, and so it will escape to the formation of a solid body, right? So based on the materials that we've seen in Bennu so far, we tend to think that Bennu is a daughter fragment of a bigger body that at some point was orbiting behind the snow line, meaning farther out in the solar system. But the curious thing is that Bennu is inside the solar system. So that means that something happened where this initial parent body that was living in the outer part of the solar system somehow first got destroyed into several pieces, and second, those pieces somehow ended up in the inner part of the solar system.
That's so cool. So it's basically got the secrets of the early solar system and the outskirts of the solar system locked in there.
Right.
And now it's close enough that we can talk about what's in there. So how big of a deal is it to have a sample from Bennu? We already have material from asteroids in the form of meteorites that have landed on Earth, right?
Bennu is in outer space under vacuum, under really cold conditions. And so anything like that crosses our atmosphere that is full of water, full of organic matter in the air, it's going to be just different. It's going to start decomposing. Actually, that's something that not many people realize, is that what we see in meteorites today, we first don't have a context of when did it come, unless you see it fall and then you pick it up, but that's kind of rare.
Right.
But if you collect meteorites in Antarctica, for example, those meteorites could have been sitting on the ice for thousands of years.
Right.
You don't know, right? And then, so you don't know where it exactly came from. Did it come from the inner solar system? Did it come from the outer solar system?
Right.
What is the parent body of it? Did it come from a planet, from a moon? So it's just random. You assume that, it's...
right.
But you don't know for sure.
So we have so many questions about those meteorites, about their origin story.
And of course, the contamination that you can escape of. You can really not escape from the of contamination on the Earth. It's just impossible.
So here we've got a pristine sample of an object whose history is very well known to us compared to those.
Right.
That is so cool. So it took OSIRIS-REx 7 years to bring a sample from Bennu to Earth. That's a long time to wait. So when you first got your hands on the sample, can you set the scene for me? What was that like?
I'm a little bit different, I guess, from everybody else. I thought I was going to be super excited, but then when the moment comes and you have to handle the material and you have it in your hands, you got to be really careful. So you got to take the emotions out of it. You got to focus on what you're doing. You got to be careful with each step that you take. And so my approach is thinking, this is not valuable. I mean, not that I'm going to throw it away or let it fall in the floor or something, right? But, be methodical about it and not so, I guess, passionate or nervous about it. Besides, there was a delay on the delivery of the samples.
Okay. So it sounds like your anticipation phase was waiting for things to get here. But then once the job was here and to do it, you go into work mode. You're going to just get the job done. And
I even told my wife, by the end of 2023, I prepared her, hey, through the Christmas holidays, I'm going to be working. I'm going to be analyzing Bennu. And so there's no vacations for us. But I guess... it is what it is.
So you're talking about the samples from Bennu and having them delivered here to Goddard and when you're about to work on it. I'm trying to imagine what that looks like. So are you in a clean room, in a bunny suit, touching rocks with gloves, or are the samples different than that?
No, absolutely. We have what we call a clean room. It's a cleanish room. It's not under vacuum or anything, but yes, we have to gown up, put in a harness, a mask in the face, gloves, and then covering the shoes. And so we get into this room where the atmosphere is cleaner, and then we have special chambers that blow clean air. There is a positive flow, so things cannot come in that chamber. Things only go out, right? And so that's where we place the samples. And so far, it's been great.
What does the sample look like? A little rock?
The samples, they are really dark. They look like charcoal, literally. You wouldn't be able to distinguish naked eye, is this charcoal or is this meteorite?
Wow.
Or Bennu? You wouldn't be able to tell. So we get the samples in what we call the Eagle containers. So the Eagle containers are these sort of metal tubes that are sealed under nitrogen gas inside a special facility unit where they curate Bennu. And so they weigh the sample there inside those nitrogen gas chambers. And then they ship them to us here at Goddard. And then we open those containers in this clean room that I was telling you about. And hopefully by that time, the sample has not absorbed any of the earth water, and it remains as pristine as possible. And so that's where maybe if we need to crash it, we crash it. That's where the fun starts.
So can you give us a sense of how long did it take to start doing these measurements in the lab? Is this something that was like a day? You had
No, I mean, it sounds like, oh yeah, you get the sample and you do analysis, right? No, the development of the methodology is very laborious because you are working with these mineral rocks that contain trace amounts of organic materials. And just think that your fingerprint will contain 1,000 more times more organics than the actual rock that you're analyzing. Right?
Yeah.
So the sensitivity of your instruments have to be tuned for that low concentration. So the challenges that we face are contamination and the limits of detections. And usually the methodology to investigate these species in our lab could take any time from 6 months to maybe a couple of years.
Wow.
And then even then, when we think that we are ready to finally analyze a sample, once you test it in an unknown material that you don't know what the mineralogy of it, you don't know its composition, maybe your method will be completely useless.
All these reasons to be so methodical, so careful, so much preparation going into these measurements. So now, okay, let's go to the moment where you're finally starting to gather the data from the sample. And this is sort of the big reveal for this sample. So what did you find?
So our first paper in organic compounds is led by my colleague, Danny Glavin. And it mainly focuses on the analysis of amino acids, although several other families of organic compounds are also being presented.
Okay.
That includes species that are important for the origins of life. And, to make a cell, you need a cell wall. And that cell wall is made of what we call carboxylic acids. And those compounds have been found in Bennu. Then inside the cell, you'll have proteins. And proteins are made of amino acids, which we have found in Bennu. And then to make life, you make RNA and DNA. And those are made of nucleobases, amino acids, and sugars. So we have the amino acids. We have found the nucleobases.
Wow.
So, and to make all of those compounds, you need other starting materials called aldehydes and ketones. And we have also found them in Bennu.
Wow.
So all of those species will be described in this paper.
What does this news mean for the field of astrobiology? How big a deal is it?
I mean, it's a huge deal for astrobiology. It confirms all the... I mean, you say, oh yeah, all those compounds have been seen in meteorites. But what about if all those meteorites were actually contamination?
Right.
We didn't know that. So now we do. And then we are confirming that the chemical inventory of the early solar system was really big, very large, and that the molecules survive and impacts on the Earth. That they could seed organics on the early Earth, that we could all be descending from the water in your body, by all means, could be coming from one of those asteroids that actually impacted the early Earth. Right. And that's, I mean, when you really think about it, that's deep stuff, right?
Totally. So these asteroids like Bennu were delivering water and compounds to the early Earth. So this is really, the astrobiologists are going to have a field day with this as well, right? It's putting lots of things that are big question marks now, kind of making the guardrails.
So if I tell them, hey, these are the compounds that were available, how can you make a cell out of this?
Wow.
What would it take? What minerals, what water level, what pH, what can you do with this inventory?
Yeah.
Right? Give me life out of this.
We're getting there, right? We're really narrowing down the space of like where we start asking those questions and pushing forward. So that's super exciting. So talk a little bit more about those organics. So what is that telling us? How do we think they got there?
Well, they before the solar system formed, we know that there was a cloud because we see clouds everywhere in the through our galaxy and through the universe. So we see different clouds that later collapse into what will become eventually a solar system. But that cloud, what it contains is dust, ice, and all the elements that you can think of in the periodic table. Right? So they are already there. And so there is a lot of radiation that is happening in that environment.
Right. From the young star, from the baby star.
Right.
Yeah.
So then while that cloud starts collapsing and forming a disk where in the middle you'll have the sun, and orbiting around it you'll have the planets and moons. Through all that process, all these chemicals, all these elements are interacting with each other in this heavily radiated environment, and there are impacts providing heat, and there is elements that provide heat through radioactive decay, and so there are different conditions that will propel the synthesis of larger molecules. So that's how we think that species like amino acids are initially formed in the early solar system from the cloud. Right. But then when the solar system is finally formed, those processes start fading away, right? Because now you have a more stable system. Right. But if you, for example, keep having liquid water and an excess of heat, the decomposition of those initial molecules that were formed from the cloud will start happening. So they will start decomposing now, not forming, but decomposing. Wow. So there will be a balance between what is made in the cloud or in the protosolar system, and what is made once the solar system is finally formed. Right. And then those compounds will be either delivered to the Earth or, well, stay in space forever. Right. But yeah. Those that are impacted and delivered to the Earth will again be modified, and more synthesis and destruction will happen. Right. So you're talking about at this period in the early solar system where we have all these ingredients that were important for life to develop here on Earth, and we had good conditions for them to be, captured on Bennu and staying there for so long. What does that mean for the larger solar system and life? Is it possible that Bennu could have developed life on wherever it was on its parent planet, or was there like life being seeded throughout our early solar system all at the same time? Well, that's a very difficult question to answer. Are the organic compounds on the Earth and on Bennu similar to those, for example, on Mars, on some other solar system bodies that are rocky, like Ceres, for example, a dwarf planet, or some of the moons of Jupiter, right? And if that is the case, if they are the same or if the organics are different, if life could evolve, would it be similar to ours or not, right? And that is a question that we cannot answer yet, right? Because we have not been exposed to a different type of life, and the chemistry will change depending on the physical chemical conditions of the environment, right, and the availability of the starting materials, right. So that is a question that we are trying to answer through what we call the study of biosignatures, right. So even on the Earth, like when we dig for dinosaur fossils or oil, right, that is organic matter that has been destroyed and decomposed, and that organic matter somehow resembles that of the organic matter that is present in meteorites, right? So imagine that we wouldn't know what life is or what life looks like on the Earth, and we were able to analyze those two different rocks, one that is coming from the dinosaur juice, right, and one that is coming from the asteroid. Right. How would you differentiate? How would you know which one was coming from life,
Right.
and which one is coming from non-life, if they are
Right.
so similar.
Wow. Yeah.
Right. So
Right.
so those are techniques that and results that we need to we are only now kind of trying to answer. Actually, in the last 2 years, this question of how to differentiate living residues of organic matter
Right.
to non-living residues of organic matter, it's been a topic that is really
Important,
growing
right?
a
It's going to
lot.
be such an important question for us.
If you go to, say, Enceladus or
Right.
Europa, and
Yeah.
you analyze the surface, and you don't see any of the organic matter that you see on the Earth, and you don't see any of a different distribution of the organic matter that you see on Earth, and a different distribution that you see of the organic matter that you see in meteorites.
Right.
Would you say, hey, there's no life here?
Can you?
You cannot,
Yeah.
right? You can say, hey, it's just different,
Right.
But we don't know. So
Right.
only by analyzing all of these different parts of the solar system,
Right.
and having a bigger database, is that we are going to be able to perhaps totally say no, there's no life there,
Right.
or hey, yeah, perhaps it's a life that uses a different alphabet.
Right. So it's basically helping us to refine our biosignatures and how we'll go after them and prune off some possibilities that aren't good, or add some that would be, ones to keep in mind. That's so cool. Can you tell us if there's anything that really surprised you about the Bennu results, or that really excites you?
Well, I guess from the organic standpoint, we are kind of surprised by the really high abundance of volatile species that it has, something that we don't see in meteorites. And we thought that meteorites were just simply depleted of these volatiles.
Yeah.
And we thought that perhaps their parent bodies or other asteroids or other parent bodies in the solar system were also depleted of those volatiles. But by analyzing Bennu, we now realize that perhaps it's a property that they lose when they go through the atmosphere.
Wow.
And only that we can only see in Bennu because it has not been altered, right? And it has conserved all these volatile species, and that are super important to create the building blocks of life. And that's really surprising. We were not expecting that.
That's very cool. And so give us an example of a volatile that you saw.
Well, the word volatile will be different for different chemists. In the organics realm,
Okay.
it's molecules like carbon dioxide, carbon monoxide, ammonia. We see a high amount of ammonia. Yeah, those are volatile species that you don't typically see. You see in trace amounts in meteorites, but not like in Bennu.
So that was a really important and a surprising thing, right?
Yeah, because again, like those species could only survive if they were solidified at certain distance outside the solar system,
right,
or outside. I should say the snow line.
Okay,
right, like far from where Bennu is currently. So that tells us about the origins of Bennu and the synthesis of those species.
Can you just say a little bit on a personal level? What does it feel like to you to have all this information about Bennu right now, after years of waiting and years of work?
Well, it's exciting. It's also I feel really grateful and humbled by that experience. Although I cannot enjoy it very much because I have to keep doing analysis, writing papers, writing proposals, and repeat. Yeah,
take that moment, right, to kind of come outside of it and really.
Yeah, I would say humbled about the prospects of doing all those analyses and having all that information firsthand.
Yeah. Can't imagine, but I'm really...
Like the other day, there was a tour visit from people from the Congress, and they went to see a tiny fragment of Bennu. It was just a tiny rock, the size of like 2 millimeters.
Speck of dust.
Right, but that same day, I was analyzing 200 milligrams of it. I had it like working and going through. I of course didn't say anything to anybody because I didn't want an interruption.
Right,
but I was like. Inside of me, I was like, hey, I may not be that important, like the Congress people, but I have 200 grams of an asteroid in my hands right now, right? So that's something that I enjoy, I guess,
That's very cool.
That thought about it, but it doesn't really matter.
Yeah. And also like just appreciating the value in that tiny little speck, right, of what you've got. That's so cool. So there's one question we always ask. What are you still curious about?
Well, I'm curious about what we could find in other asteroids, in samples from that we could bring from Mars, from the moon, from other asteroids or comets, or from moons in Jupiter. I am excited about the future, and I really hope that these techniques and methods that we have developed and applied so far could always get more improvement.
Right.
And I hope that we are seeding what could maybe in 10, 20 years, we'll say, hey, other people smarter than me has used my techniques and make them better, right?
Very cool.
And that would be super, super exciting to me. I would feel great.
Awesome. Jose, thank you so much for talking with us today.
No problem. Thank you for having me here.
That's Jose Aponte, an astrochemist at NASA. This is NASA's Curious Universe. This episode was produced by Christian Elliott. Our executive producer is Katie Conans. The Curious Universe team also includes Maddie Olson, Michaela Sosby, and Jacob Pinter. Christopher Kim is our show artist. Our theme song was composed by Matt Russo and Andrew Santaguida of System Sounds. Special thanks today to the OSIRIS-REx science team and to video producer Dan Gallagher. If you're interested in reading more about the science results from Bennu, go to science.nasa.gov/mission/OSIRIS-REx. That's OSIRIS-REX. And if you can't get enough of asteroid science, check out our 2023 episode, Special Delivery from Outer Space. Our producers captured the nail-biting moment when the OSIRIS-REx spacecraft dropped its Bennu samples to Earth. As always, if you enjoyed this episode of NASA's Curious Universe, please let us know. Leave us a review, share the show with a friend, and remember, you can follow NASA's Curious Universe in your favorite podcast app to get a notification each time we post a new episode.
Three, two, one.
This is an official NASA podcast.